Okay.
What happened?
There was this car, it was just acting crazy, and it almost hit my sister and I when we were coming in. And I'm speeding up, slowing down, and it's just matching, and it almost pushed me into like the little railing on the side.
Today?
They
Just now?
was the bit shaky.
It is crazy. Yeah.
Crazy drunk.
Yeah. Well, hope this class will calm you down. All right. Welcome back, everybody. So last week was a little unfortunate. I thought there was going to be a storm. Not really. So, but, you know, as a result, we skipped the class. We didn't have to, but oh well. I hope the video was helpful. So here's the plan. Oh, by the way, you know when the final exam will be? It's on the syllabus. It's May 4th, and during class time. This is not accurate information. It's May 4th, similar to the midterm. 90 minutes, right? We'll start short after the class starts. Hey, so that's that. Last week I was going to talk about the top portion of these points, mostly a background of text mining, unstructured data, unstructured data science. Here is we're talking about text mining. And there are other kinds of unstructured data mining, but we're not covering those. Text mining is a growing field, becomes more and more useful, and that's why we're learning it. The video that I released mostly focused on a background. You know, why is text mining useful? You know, there's some business scenarios or some motivations for that. And then it spent a lot of time talking about the messy symbols in the text data that you collect from the internet. I talked about and a scraping project that I did on Yelp in the video as well. Right. So just a recap of what was covered. And then I spent a lot of time on how to form a strategy to clean the symbols that are not meaningful in the web data. Right. All of those are basically the HTML tag syntax that somehow, got mixed into the data that were collected from the web. And that is inevitable. You will, sooner or later, if you scrape data from internet, then sooner or later, those symbols will go into it. And those symbols will become source code. HTML source code becomes harder to remove. A very simple, greater than symbol, greater than, becomes the codes. So, and those codes get mixed and mingled into the meaningful text. The content on the web becomes harder to remove. So that was a big part of the cleaning process. As we say, in a data mining or machine learning project, we spend 60% of the time cleaning, pre-processing, dealing with all kinds of data issues. We only spend 40% of the time and energy in the real steps, So this is ironic, but this is reality. And same thing goes here. Cleaning web data is not straightforward either. So that's why. Over there, the strategy is to use regular expression, but it's important to understand, main features of regular expression, and then how to use it, the character sets, those concepts. If you don't go deep into it, if you don't analyze scenarios, it's not very intuitive. And today I plan to go through some of the questions in homework 4. And then we'll have a chance to get into it. Hopefully you have studied this part so that today's discussions, today's focus on the homework questions will be meaningful. Otherwise, you're just listening without really getting into how it works. So that's the first part. It's a review homework 4 on cleaning HTML symbols. But before we get to that, there are some questions in homework 4 that deal with the previous chapter, the model evaluation. So we'll go through those as well. Homework 4 will be due next week. We'll cover hopefully most of it, but we'll leave some of the questions to next week. That will be mostly about the modeling part, the hardcore modeling and the hands-on implementation of this LDA model. Hopefully we'll have some time today toward the end. I'll go through, or I will highlight the concepts that goes into this model. This is a classic text analysis model, text or natural language processing algorithm. It's a model, it's an algorithm in the sense that regression is a model, neural network is a model, and then LDA is a model. The model has a few, principles and foundations. It uses the backwards. We'll get into it later. So that's the plan. All right. And let's see. Cleaning the text is not here. Cleaning the text, we use regular expression. So these are the basic points that in the video I talked about. I was going to talk about last week if we had class, but that video served the purpose. Now, let me switch over to the homework. Miguel, can you read the screen?
Yes, I see it.
Okay. Um, so. Right, hopefully, you have your homework open and let's follow along. The first three questions deals with the model evaluations. The first question is about analyzing the two kinds of errors specifically related to the target class. Right, so here the context is the same. We're dealing with a binary classification problem. There's a positive outcome, there's a negative outcome. The problem here is spam email. Spam emails are those emails that sometimes has advertising, sometimes it's phishing email, sometimes I don't know what else. What kind of spam emails have you experienced, and what kind of spam emails you find annoying or bad, evil? This is evil. What kind of evil spam emails have you seen? Huh? Say it again.
And I think my friends want to send you millions, but
It's like a scammer, they like ask you to send like $10 and then
Scam.
send you like $1 million.
So fraud, credit card fraud. There can be different kinds. I have received emails that look like I believe it's eBay bills. So, I have a bill, I have a balance, I have to pay. You're talking about that? Same thing? Or something different? Yeah, that you were trying to say.
some email that tells you that he has like some funds in a bank, that he can't get them now. He will send you the funds when you need to pay some fees.
I see. It's a classic scheme.
Yeah.
Do they have a name? Maybe, maybe not. I rarely see that now. Maybe it's easy to recognize and it's filtered, So email servers have a filter function. Gmail has Gmail's own filter. The school email, Microsoft, has Microsoft email, spam filter. And if an email is tagged as spam, it's, it skips the inbox and it goes to the spam folder, right? Sometimes go to, I believe it's spam folders mostly. Gmail has a spam folder. Do you check your spam folder once a year? Maybe once 2 months, every 2 months, because you can't find something. And then it's important, right? So you check there, but it's not there. So it's given that we don't check spam emails, spam folder very often. So that's a given. So that means if something ends up there, which is important, it kind of, we don't realize that. We don't know about that. Unless somebody reminds us to check spam, right? So that's an issue. On the other side, if a spam email goes into your inbox, unfiltered, when you look at the email, how likely do you think you're able to recognize it's a spam? Fairly likely.
Really sends from a Gmail account. They're talking to a company. And sending you an account. It
Would be,
will be a scam.
can be a scam. Right, that's what I'm asking. If it's a scam, how likely do you think you'll be alert? Or on the other side, how likely are you how likely do you think you'll fall into the trap? If something is brand new, maybe, but that doesn't happen very often. It's most likely, the known kinds of scam. It's just being used over and over. So I would say quite likely I will be alert. Myself, get a lot of spams. I don't know why, but and nowadays mostly on cell phone. I get text messages, and then the moment you see it, you recognize, so it comes in different forms. Your spams and my spams are probably different, but it comes over and over and it repeats itself. So it's annoying, but that it's what it is. You can't completely solve it, but it's fine. So these are the kind of thoughts that will go into this question. In terms of spam, can you tell me the positive outcome? What is the positive outcome? Here, positive and negative doesn't mean good and bad, as we talked about. Positive outcome would be the outcome of primary interest to our analysis, to the problem. So what is the positive outcome? Spam. And what will be a false positive error? So exactly, it's a negative, but it's incorrectly classified as positive. That's false positive, and false negative is the other side. In the case of false positive, what does the server do? False positive. Server detects a spam, which in reality, it's not a spam, but server thinks that's a spam. What does it do? Like what we said, skips the inbox, goes into spam folder. And we don't check it every day, right? We don't get an alert. The sender does not get an alert, okay? This is false positive. What about false negative? What is false negative, by the way? It fails to detect the spam. It is a spam. Server fails to detect, and what happens? Goes to inbox, we will see it, most likely. Oh, by the way, it probably goes to the other tabs. I use Gmail a lot. I look at every email, including the social media promotions but now we have different tabs, right? Do some of your inbox have thousands of unread emails under those tabs? Yeah. So you don't read every emails, and that's fine. If a spam goes there, if it's a false negative, probably doesn't waste your time. That's cool, right? But it doesn't always go to social media tab. It doesn't always go to promotion. If the server missed it, then it typically goes to the personal tab, because likely the server thinks it's important. It it passes the filter. And then we see it, we read about it, we recognize the spam or the scan, and we're alert. We move it to spam, and story is over. So that's what happens in the case of false negative. Which one is worse? Which error is worse? False positive? You think false positive means move it to spam and we're on alert? It goes to spam, but it's not spam, it's a ham. And then we're unaware of that, and it goes there, it stays there for a long time before we find out. If it's an important matter, or if it's an urgent matter, then the consequence might be bad. I agree. Yeah, I agree that false positive error is worse than false negative. There can be a debate. But I think more would agree that false positive is worse than false negative here. What do you all think? Yeah, good. So, use the same method to analyze questions like this. Every business case is different. All right, the next two questions actually build on the same example. Here, I give you a confusion matrix. The confusion matrix is structured by using the same convention. The columns are predictions, the rows are ground truth, the actual labels, and 1 means positive label, positive outcome. Positive outcome always come first before the negative outcome. So positive outcome on the left or on the top. Then the diagonal line would be that, backslash direction. So the question asks you to calculate these by using 2 methods, if possible. Those in blue means they can be calculated by using 2 methods. One is manual, by hand, by using formula. The other is by using some kind of function provided by scikit-learn. To calculate some of these, you would need each of the cells, right? So for the first 4, you actually assign the right number to it, and that would be all. No calculations involved. But then for the rest, if using formula, strongly encourage to use these names to simplify the process, to standardize the process. Tony. All right. Now, based on this confusion matrix, this is homework 4. We have TP, TN, true positive, true negative. We have FN, false negative, FP, false positive. Tell me what is true positive, TP. $380. Nice. Tell me what is false negative. 20. Tell me what is true negative. And the other one is, which is FP, right? False positive. So be super clear about these. And then what you're going to do is just to give them the values. So I'm going to do it here. Let me run these. This simulates the data set. All right, so I'm just going to punch in TP 380, right? True negative 1315. I can't see it. FN 20, I remember. FP true 85. Wow, that's large. All right. So you have the first 4. And then at this point, typically I would recommend to calculate 2 additional quantity that is not being requested. But having those quantities will be useful, which is P and N. Capital P and capital N, which means the true cases, the true positive cases and true negative cases. True positive cases would be TP plus FN. All those cases that are true, but qualification might make a mistake. But regardless, those are true cases. That would be the sum of the first row. TP plus FN, right? So that's positive. Once you have TP, once you have the 4 elements, you can simply refer to them. TP, FN. And the negative case would be TN plus FP. All right. Now run that first. And then we can calculate them by order. Part 5 is error. Let's do error. I'll stick to the capital letters. So error, remember the formula, or remember, how do you get error? Error would be, oh, by the way, it's not necessary, but something else that can be useful is to calculate the total. And since you have P and N, you can simply use P and N. And makes the formula easier. That's it. So error would be something divided by the entire sample size, which is the total. Would be the 2 kinds of errors, the sum of 2 kinds of errors on the top, right? On the numerator. Which 2 errors? FM plus FP, exactly. Divided by total. Right? So that's error. And 6 and 7. So this gets a little bit trickier. False negative error. False negative error would be false negative on the top. That's straightforward. But what goes underneath? P. Great. That's the benefits of having a P. So whenever we talk about error, what goes into the label is actually the opposite from the truth, right? So what you want on the denominator is the truth cases. Good job. So false negative error would be false negative minus divided by the true cases, positive cases. And then by same logic, false positive error would be false positive divided by and the total number of negative cases. And 8 is accuracy, true positive, true negative. Okay. Now, accuracy. Accuracy is the opposite of error, right? Or it is the number of true predictions, including true positive and true negative. So you can do it, one of two ways. You can do 1 minus error, or you can reconstruct the formula. True negative plus true positive over total. And now comes the true rate. True rate is also the 1 minus the other side, but the label don't always align. But from the formula, true positive and true negative rate is more straightforward. True positive rate would be true positive on the top. That's straightforward. And what goes to the denominator? Also positive cases. So it would be 1 minus what? So let me complete this formula for first. So it will be 1 minus something, but that something should have the same denominator. So it will be the 1 minus false negative, right? So true positive, the other side is false negative. And true negative rate is true negative over the negative. So the opposite side is false positive here. All right, and precision question. I have TOL, TLL. Sorry about that. TTL. Good. Thank you. Yeah, you just save me from a heart attack, So when I run it, it's going to give an error, I'll get a heart attack. It just saved me. All right, precision is positive prediction value, positive predicted value, precision. It focuses on the column, not the rows anymore, right? It focuses on the predictions. So it is the what goes on the top, the correct positive predictions divided by what goes to the bottom. And now, is there anything that we can use that's calculated sum on the denominator? What goes here? TP and
F.
TP and FP. So both correct and incorrect. Positive predictions. You need a parenthesis here. Both true positive and false positive, and there is no such a sum previously calculated. All right. And the last one, F1 score. F1. Let's do that. Keep it consistent with our notation here. So F1 has, just apply the formula, and we should have everything here. 2 times TPR, true positive rate, times precision, TPV, divided by the two put together. So I believe that's correct, right? All right, and if it runs, it doesn't mean there's no mistake. There could be a mistake. So what I always do is to put in some kind of sanity checks. Of course, you can compare, by looking. But some of the easy checks are that if my P and N put together equals the total, it should equal the total. But what if I type it wrong? It will not. Well, no, this time it will equal. That wouldn't work because my total is the sum of P and N, and P and N are the sum of that. So what I want to do is, I know the total sample size is 2000. So I want to check that I use a CERN, it works, didn't complain. So at least that part is correct. And then, as part of the question, you want to print them out. So use the same format. So you can do you don't have to print the first 4 because that's very straightforward. But beginning with error, it's better to print them out. Error is, and then, I think what I have been using in the course is to use f-string. When I use f-string, I can execute code within the string, within the print command, and then I can put commands, variables. I can do calculations. I can execute codes within the curly braces. So I have error, right? So for just to print out this example, that's my error. And you can put in some kind of format. I may have used this in some of the modules, but if I only want to keep 2 decimals, you use comma, not comma, sorry. What is that? Colon. You use colon, followed by the format. 0.2 means 2 decimal points after the decimal. And then it's floating point. So, to keep it simple, you can do 3 as 3 or 4. And then follow the same format to print the other things so that when we grade, it's more efficient and it looks nice, right? All right, so that's by hand. But what about, I'll do it here since this is too long. Obscures the view. By programming, you can only get 5 of these by programming. See? You will be able to get PPR, which is recall, sensitivity recall, and FPR. You can get FPR together by using the ROC curve. It's the ROC curve. Right. When you use the ROC curve, underscore. When you use ROC curve, you need to provide 2 things, 2 data. You need to specify the true values and the predicted values. All of them come from the simulated data set. So DF, Y true and Y pred of DF. So DF, or use dot to, access the attribute, which can also access the column. Y true, Y pred doesn't. It doesn't come out. Okay. All right, ROC curve, and then according to the tutorial, you'll get 3 outcomes. The first 2 are useful here. The third one isn't very useful. Is it too small? Okay, want it bigger? You'll get 3 things. The first thing that you will get is actually false positive. Let me double check. Oh, we will need to import. No, it's already imported. ROC curve. Okay, great. So the first thing you will get is false positive rates. And let's denote that as by using program. The first thing that's returned is false positive. The second thing the return was the recall. And the third thing, we don't care. So by that, we will have the FPR and TPR. Okay, and then next, let's get to accuracy. Accuracy, we will use the same thing that we used for all the models that you learned, the accuracy score. And for the same thing, you will provide true values column and predicted value columns. What you can do, if you are sure about the order, you can remove the parameter name and simply provide in the correct order. All right, so that would be complete for accuracy. And then we have FPR, TPR, and then we need to calculate PPV. PPV, there is a PPV score. There's a precision score. Sorry. It's essentially precision. precision score, you provide the same thing. As parameters, the data. And the last one, F1 score, has a F1 score function. And then you'll provide the same thing. All right, so after running this, oh, I just had a heart attack. There's a typo for sure. See, what is that? OC curve. There is no Y bread. Are you sure? Oh, okay. It's called Y score, not Y bread. Score is prediction. All right. Ooh, I'm back. Anyway, so I'm not trying to say it's bad. Errors are good. You need to be able to understand errors. The error logs, the error message, the pointers, the information that comes in the error. It helps you debug. So, you know, don't be like me. I'm old. I don't like heart attacks, but you're young. You can take it. So analyze errors whenever you see them. All right, they are very helpful. Okay. So as you already know how to print all of these, I will not illustrate all of them, but I will print out those that are calculated by formula versus those by program and make sure they are the same. So I'm going to do the TPR. By hand and by programming. Okay. And then we'll do the same. For all 5 of them. I have, what else do I have? FPR. Okay. Accuracy. And I have FPR. You don't have to follow me exactly. I'm doing this just because I want to check the 2 results are the same. What else? PPV. And F1. F score. No, F1. Okay. Okay, and then I want to control the format. So we paste. Quickly review. I'll move this up. Move this down. so that it follows the same order. FPR, accuracy, PPR, PPV. Okay. Whoops, again. You see anything wrong? Unsupported formation. Fine. That makes sense. So I get an array. So it's okay. I see. Now, so there is indeed a trick here. Calculating the measures from ROC curve, these two actually, they are not scalars. So let's take a look. It's an array. This is an array. So for whatever reason, the way ROC curve returns these outputs, it serves a different purpose, but we're repurposing the function. So what happens is we need to extract value at index position 1 for both of these in order to get what we want. So for both places, we need to specify the index value 1. All right, so in order to really do this correctly, you want to add these commands. Okay, so these are the correct ways of doing it. And it is easy to forget, but you know, if you follow the tutorial or if you follow the homework assistance videos, you would have notes about these. So doing this would solve the problem here. So, you know, quickly compare that these calculations are the same. Okay, so that is all for this question. But in order to answer the following question, it's also helpful to get the value for false negative. Because we already have false positive, but we don't have false negative here. So we use the FNR calculated by hand and print the result. Okay, once we have these results, we can answer the following question. Any questions here? No, no questions. Good. Okay, so what's the error? Error is 15%. It makes mistakes on every 15% of the predictions. But when you look at the different errors, FPR is 17.8%. It's slightly over the average or the overall error rate. This video is recorded, by the way. You can, you can go to Teams to review it afterwards. But just so you know, FPR is above the error rate. But when you look at FNR, false negative rate, it's much below the error rate. All right, so it makes mistakes. It makes mistakes on the false positive side much more frequently than on the negative side. or the negative side meaning misclassifying as negative, but it's actually a positive case. So the next question asks you to analyze this model. This is a problem of churn prediction. Now, you'll be very familiar with churn prediction through the homeworks. In a churn prediction problem, what is a positive outcome? Churn, right? Churn is when a customer leaves the company or doesn't renew the contract, which means a loss for the company. And for the company, if there's something that you can do, you probably should consider it. A discount or some sort of promotion or some kind of extension of benefits. It's a small cost, small sacrifice for a bigger return for the company, right? So the positive cases are important like cancer. It's like cancer, right? If you can detect cancer, you'll do something about it. And in this case, which error is bad? Which error is worse? False positive or false negative? Think about it, let me know. False negative is worse. Tell me what false negative means. The churn is the positive outcome. The interest is to predict churn. Or makes a mistake in the prediction, right? The algorithm, in the case of false negative, right? The algorithm predicts negative, but it's an incorrect prediction. It's actually a churn, right? So churn misclassified as loyal, right? The opposite side is loyal, right? Loyal customers. Right, so that's the false negative. Why is it worse? Think about what happens in this case. What's the company policy when the algorithm suggests that this customer is loyal? Think about the cost benefits. Think about what the company does or will need to do in the case of false negative. And it helps to also think about the other side, false positive. False positive is when this customer is loyal. It's not a churn. The customer is loyal. Algorithm thinks this customer will churn and report that, report the alert. This customer is likely to churn. Algorithm reports to the management team. What does the management team do? To do something, right? To do something to persuade the customer to stay, right? So you would inevitably will give up something. The company will give up something, a discount, a promotion, something like that, hoping that this is enough to change the event. Right? So think about the consequences. False positive. I'm the customer, you're the company. I'm staying, I didn't tell you. You think I'm going. You think I'm leaving. So you beg me to stay. You give me a discount. And I'm thinking, wow, it's money coming from, falling from the sky. I'll take it, of course. So 5% discount. Let's say if the contract is $1,000, I get $50, right? And then I'm happier, I stay. We don't consider any long-term effects. We only consider this instantaneous analysis. So as a company, you lost $50, but you helps. Maybe it didn't help, but at least the contract is secured, right? So that's a cost benefit. The loss is $50. On the other side, false negative. I'm going to leave. I didn't tell you. You thought I'm loyal, right? So you don't send me a coupon. You don't do anything because you think it's okay, right? You assume revenue or profit from this customer, but in fact, you are going to lose the customer if you don't do anything, right? So the likelihood of losing this customer is high, above 50%. And the lost contract is $1,000. We typically multiply the likelihood with the dollar amount. That would be the expected loss. And the expected loss would be more than $500, right? In this case, in the case of false negative. So the costs to the company in case of false negative, $500 or more. The cost in the case of false positive is $50 we talked about. Which one is worse? False negative, right? So in the case of detecting churn, you would want the algorithm to be easy on false positives. You would kind of want false alarms. It's like detecting cancer. You like false alarms than negligence, right? Same thing that we talked about. It's like fire alarms. You want more false alarms than undetected fire. So same thing with churn prediction problem. So that is what you are going to analyze here. Typically, to answer these questions, you need to state what is positive and what is negative, and then state what is false positive, false negative. What does it mean? And then analyze what does the company gain or lose in each case. You don't have to specify specific dollar amounts. You don't have to specify the likelihood, just like I did. You don't have to. You simply need to make a case that the potential loss in the two cases, they are clearly different. One side is clearly more than the other. In this case, it's false negative. The potential loss is one customer with a contract renewal. That's huge. The other side, false positive, the potential loss or potential cost is just a coupon. So that's clearly different. That's how you draw your conclusion. That false negative is worse. Any questions? All right, with that, that's all the questions that is from the previous module in this homework. And maybe we get started a little bit and then we go into some kind of break. The next set of questions is about cleaning the unwanted symbols for data that comes from the web. This is a very small data set. It has a few paragraphs about politics. Hope you enjoy it. So let's take a look at the data set. It has only 2 columns, it has only 5 rows, and we can print the rows. Okay, so 5 columns, index value goes from 0 to 4. And the content here, you can see that it's quite messy. It is the first one, if you're familiar with HTML, if you take a look at this, then you kind of, you know, have an impression that it's kind of a table format, but not exactly tables. It is text with a lot of breaks and some spaces to try to align the text into the same column. So, but since there are a lot of breaks, line breaks and gaps, you have a lot of these HTML symbols. Each HTML is organized by tags. The tags are marked by the pointy brackets, the less than symbol, and then the large than symbol, the greater than symbol, right, as pairs. They have a lot of these. If you take a look at the source of this, then, you know, the less than and the greater than symbol is the most prevalent. This is HTML. And the unfortunate thing is when you collect data from internet, a lot of these gets, you know, mixed into the data. So the job is to clean all of these to maintain, to retain meaningful content and remove these symbol strings. The second one doesn't have any, which is fortunate. And so here, this one question has 4 parts, but mostly has 2 parts. Asks you to analyze 2 sets of symbol strings and then understand the pattern, come up with a pattern, and then fix one type at a time. Afterwards, all of these symbols will be gone. Right, and it is, you know, I use this as sort of a review of the video I released last week. Hopefully you had time to go through those to understand. All right, in the first set, it deals with symbols like these. Wait, let's not run it. Okay. Could be this. Work. Anyway, so ask you to come up with a pattern for regular expression to identify all of these different examples. So how would you construct that pattern if you have reviewed the previous week's content? These are all tags, and in fact, GT semicolon, it is the source code for the greater than, GR, greater, GT, greater than. GT semicolon is actually greater than. But in HTML source, it gets, kind of translated into the source code. So if you replace all the GT semicolon, all of these are tags of different kinds of tags. You have break, you have a div, you have a tag, which is the link, HTML links. And then the other half, you have span, and you have B is what B is to bold, right? So all of these are tags. You want to remove these tags. You cannot simply just remove the less than symbol, because these BR, div, they get mixed into the text and then becomes a distraction. These are not meaningful. These will be recognized as typo or, misspellings, and which makes it harder for text mining steps. So if these are well recognized tag symbols, it's best to remove them. So how would you construct the pattern? In the video, I talked about symbol sets, character sets. That would be, one of the best tools that you should use. And together with the repeating patterns, that would be it. That would be mostly. So you want to recognize the parts of the different variations of the symbols that don't change. That happens always, all the time. Typically the beginning and the end. Observe the parts, observe the symbols that these different examples always begin with and then always end with. Recognize those strong patterns and then include it in your pattern construction. So that would be the first step. So let's say pattern 1 is, and all the patterns will be included in quotes. It's a string, but regular expression will recognize special purpose parts. I'll talk about that. So here, observe these different examples and which paragraph has the most of it. The first one. You see a lot of tags here. There are a few tags here, but not a lot. Some of them here, a few here, a few here. The first one has a lot. So across these different examples, it always starts with what? It's a tag, right? It's always start with the less than symbol. So you want your pattern to start with that. Anything else, or any other tags that start with something else is not the job of this pattern, such as there is something like that. This is another symbol. It begins with the ampersand. That's another kind. It's not going to be recognized by this pattern, but it's fine. We can construct multiple patterns. This pattern always starts with less than, but should you include anything else? Escape? Escape what? Yeah, I mean, why do you want to escape? What do you mean?
stop with this.
I don't understand what it means. You use escape when you want to, to recognize something, but that something is a reserved symbol. So like escape bracket, because bracket is used for character sets, it's reserved. So without escape, it's not going to find these, brackets. If you want to find brackets itself, you want to escape it. That's the purpose of escaping. As far as I can see, these examples don't have the brackets, so that's not something that you want to find. Semicolon is the ending part, right? So you're trying to say, let's say, something happens in the middle, but this pattern always ends with something. Okay, let's see. I see semicolon in every single example. That's a good one. But can you include anything else to make this pattern stronger? If you see a pattern that happens on every example that you want to include it, because that strengthens the pattern. And then the benefits is that you eliminate rooms for false positives. When you recognize the pattern, programming thinks that's the pattern. It thinks that detects it. But some of these might be a false positive, which means it's not a tag, but recognized as a tag. The stronger your pattern is, the less room for false positives. I'll try to illustrate in a little bit, but try to see the ending pattern that happens on every single example. GT happens everywhere. So you want to include GT here, then leave them out. And the reason is, let's say, so if we compare two different ways, okay, these spaces are there just to align things. They don't mean spaces per se. Here, there are two different ways to construct this pattern. The first one is stronger because it has more restrictions. It includes more symbols as constraints. The second example doesn't have those letters. The ending pattern only has a semicolon. So let me quickly walk through how does a regular expression works with the patterns. Let's take this one. So always begin with the less than, and then always end with the semicolon. So what happens on the algorithm is it starts searching from the very first letter for the beginning pattern, and it finds it, the first one. All right. And then, because it matches with the beginning pattern, it will then switch to look for the ending pattern, the semicolon. But the thing is, it's trying to be efficient, and it's trying to, I guess, use the least time to find the most things, So, and assuming this is a word that we're trying to, this is not a word, it's a symbol string. It's a string of several symbols, right? And it potentially can be very long, right? Because we're not sure. Some of the examples have long symbol strings because there's a link here, or you know, etc. So it can be long. What happens with regular expression is once it finds the beginning pattern, it goes to the very end to find the ending pattern. If the ending pattern is this, then it potentially has a match of this very long string. This very long string, you know, that potentially matches this, okay? And then it do some checking. What does it check? It checks whether or not these symbols in between satisfies whatever you specify in the middle here. So, and these patterns are not done yet, but we have the beginning and the end. All right. So the algorithm is going to check whether or not this long string in the middle satisfies. So the reason I said be more specific if you can is that, let's say, what if it's not GT in the end, but it's regular contents. You know, let's say not part of the string, and this semicolon could be something that writes something that somebody uses in their writing. It's healthy content. You don't want to, you know, detect as these symbol strings. Those are real content. You don't want to filter out. And semicolon is frequently used in people's writing, right? But GT semicolon together is less likely to be something that people write about, right? So with more restrictions, especially if you confirm it happens on every you know, every example of the symbol string that you want to detect, you want to be more specific. All right, so that's that's one principle. So the first version would be preferred. Now, however, without specifying anything in the middle, let's say, if the pattern is constructed in a way that it starts with less than, ends with GT semicolon, it can be anything in the middle. Then the consequence is that this whole thing will be recognized and then could be replaced. But there are important content here. Biden, Trump, Arizona, Biden, you know, so these are statistics. You don't want to remove them. You want this instance to kind of end here and then finishes one bind and then go to the next one, beginning with this tag and then, you know, closes before Trump. So all of these are individual symbol strings that you want to recognize. So you want your pattern to be able to do that. And now we need to use the character set. Character set is used to include different kinds of symbol strings. What are the kinds of symbol strings that you see in these examples between the beginning and the ending part? It can be anything, or it could be anything. Potentially, it could be anything, right? It can be spaces. It can be letters. It can be uppercase, lowercase, potentially. It can be also slashes and ampersands. All of these different things. So it's kind of everything. The symbol set for everything would be \W would be the alphanumeric plus the underscore, and then all the white cases, all the white spaces, and then, you know, and then all the other punctuations, like let's say maybe ampersand, backslash, maybe a percentage. So, potentially a lot. You can specify all of them. But you want your algorithm to be able to stop here, not here. What is and here is when the caret symbol will be helpful. When you use a caret symbol, anything that goes after that would be the exceptions, which means don't include these. If I say alphanumeric, including all the letters, but except A. So whenever it sees A, it will break the pattern, right? And then this is, repeated for many times. This after means this character set. Whatever it falls into the set can be repeated multiple times. This caret set, this caret symbol to specify something as exception. What is it that that you should use as exception to break the pattern? To avoid the pattern from going this long, but only stays here. What you want to do is to analyze things that come between the immediate, let's say this immediate ending pattern and the last immediate pattern, something that happens here that is only part of this pattern. It's kind of confusing, but you want something to break the pattern, and the component that will break the pattern would be the beginning part. So because the pattern is only for the tags, the beginning of the tag that means a new tag, right? The beginning of the tag is a new tag, and hopefully the content doesn't have that symbol. Hopefully the content doesn't use that symbol. So this character set potentially can include everything, but not the beginning. Not the beginning character. So here's what goes on. Go and find character string. Go and find symbol strings that begins with less than, ends with greater than, but as long as there is a less than symbol in between, shorten it. All right. So this is what happens. Find the beginning pattern, find the ending pattern, always go from the bottom to be efficient. Find that, but then as long as there is a this exception here, as long as there is a less than symbol in between, shorten it. Shorten it, then goes to here, right? That's the second last ending pattern. And then find if there's any exceptions. There is exception, then shorten it. There is exception here, shorten it all the way to this point. And then there is another exception. So it shortens. Then ends up here. This is one thing that it finds by using this pattern. So we can check. This is df1 ilog, df1 ilog first. Let's see. So this is the example, and by using the regular expression, find, to be able to find just one. Okay, find pattern. Usually the order goes like this: find a pattern in some kind of string. So find pattern in this string. Let's see. And then since it will find a lot of them, I'll simply get the first three. Pattern, typo. Okay, so the first three found are these. Exactly the same. So how can I make sure it is what I said it is? A lot of these. I don't know, how do I check? Or what we can do is, if I remove this, if I remove, let's say, well, character set, I have to include something. So if I do string, alphanumeric, white space, and then percentage, ampersand, slash, okay. If I use this pattern, and then let's see what it found. Let's see. Must be something that breaks the pattern. Spaces. Maybe spaces. I don't know. Out of range. Oh, didn't find anything. Anyway, the point is that when you construct a character set to repeat multiple times, the critical thing is to find the symbols that recognize the beginning of the pattern and typically include that in the complement set. So in this case would be caret the exception. And then once you have that, print this as a way of checking the answer. And then the second part of the question will be to use this pattern to replace everything that you found with that pattern, to replace it with space. So we will use our regular expression that sub is to.
Excuse me. Oh, sorry.
The order of the parameters here would be to use pattern. So pattern goes first. Let's see. Pattern goes first, and then the replacement string would be that will come next. Replacement would be space here. And then in what string? So here it asks you to only replace this string. And then any options you want to specify. Here, typically, if the symbol string can be long, and there can be uppercase and lowercase in between, typically we would specify flags is the options. Typically we would specify ignore case. So uppercase or lowercase will all be selected. And so potentially the capital letter GT would also qualify as a pattern. Right? And you want to give it to my text 1. and then print out my text 1. So in this case, you compare with the desired outcome, it should match. So in this case, what were detected were these line breaks and a few more line breaks here. So before, yeah, we should not expect any of that. Although we do have some remaining character sets, or not characters, the symbol strings, and we will try to deal with them later. One thing to mention, these symbol strings, when you call them, they are raw symbol strings, but when you print them, they will get printed, and then they will display the symbol that it represents. So the GT semicolon will probably be printed as the greater than symbol. And here, so sometimes it goes undetected. When you print them, you can't find them, thinking they're gone, but they're actually not gone. Here, the ampersand pound 039 semicolon, when you print them, they become something else. Doesn't go away. Interesting. It goes away for me. Sometimes it happens. Anyway. Okay, so that's it. Then you have the third part of the question that deals with the second group of symbol strings. And observe the pattern here. Same thing. Beginning of the pattern, ending of the pattern, be more specific, be as specific as you can, and then construct the pattern. And always include the pattern in quotations. What would be the beginning of the pattern here? So you will always have a character set repeated with multiple times. The beginning of the pattern here. What do you recognize? The ampersand. It's called ampersand. And then after that, there can be pounds, there can be characters, there can be letters. So there's no more to specify. And the ending of the pattern is only one semicolon. Okay, so what goes in between can be anything but what. That's the critical part to, to specify. It can be anything but the beginning of the pattern, just the ampersand. So let's see. Okay. There's a special case here, which is in the earlier case, the pattern is strong in the sense that the end of the pattern has some characters and a semicolon. So it's a stronger pattern. You don't have in many cases, you don't have many false positives. With this pattern, the only end of the pattern symbol is the semicolon. And then with that, it's kind of easier to include normal text into the symbol strings. It's more likely to make that kind of mistake. So sometimes what we can do is we can include semicolon in the exception set. So think about what it means. If you don't include it, then you could have a normal text, a paragraph, normal text that talk about, that's the content, web content. As long as it doesn't have the ampersand, it will all be included here, right? And let's see. And in web content, how likely is it that you will have ampersand inside the content of the web? So if to be more specific, you can include additional semicolon here. Sometimes it will be more, I guess, more effective if you include more exceptions here. So, those would be the edge cases. Let's test whether or not we need that. Okay, so with this pattern, let's see. Ooh, interesting. Okay, so without the semicolon, what happens here on this example is that it finds multiple symbol strings that, otherwise that you would technically break them, right? This long string, it begins with an ampersand, and then it finishes with semicolon, but it has multiple semicolon in between. So what happens is it recognizes several symbol strings, but lump them all together in one. Ideally, you would like to break them. Ideally, you will like to break them. So this way, this pattern kind of over filters some of the symbols that you don't intend to include. To fix that, what you can do is if you include a semicolon in the exception set, then it will check whether or not the exception character is within the recognized symbol string. If it is, it will shorten it, as we said, right? It recognizes that, it will shorten to this point. It recognizes again, it will shorten to this point. So after you change that, this result will change, and it will only recognize the quotes. That's the difference. So, the point of having a stronger pattern is that you avoid over generalizing the pattern and avoid false positives. That's the point. You can do experiments and change things like that to kind of have a better understanding. So this pattern would be good for now. So with that pattern, let's further work on text 1. My text 1 is to use regular expression, the sub, and use pattern 2 to replace with space in my text 1, and then again flags is regular expression done. This is ignore case. Okay, run that, and then run my text 2, and by now all the messy symbol strings are gone. All right, hopefully that makes sense. Now let's take a 7 minutes break. We'll come back 7:50. Question? work. Hey, Tama. So when you have time, please try to make it with Eva. The first session, I think she will send you more information, but the point is to observe you go through midterm exam again, and to see if there's anything that she can help with sort of improving the programming process. Yeah, I hope that's a beginning beginning point.
Yeah.
Okay. Yeah.
Sounds
Try
good.
to make it as soon as you can.
Yep. Thanks. We can talk after.
Sure.
Class. Yeah.
Can you think of a way to construct a pattern that will take all the way from that here? I was trying to make it happen. You know, the point is not, I mean, it's not the way to solve the question, but the point is to show that the regular expression can be so powerful that if you don't limit it, it's going to take too much. You know, it's going to overgeneralize a lot, but it doesn't seem to happen so often or so. And in this case, or maybe the semicolon is not. Oh, for sure. Yeah, I need to include the semicolon. So let's see. So I have all the alphanumeric, all the white spaces. I have symbols. Let's see, ampersand. Slash. Pound. And then semicolon. So, you know, imagine that if there's a way to include everything possible that you can think of. And then use this pattern to one, two, yeah. One. Okay. 0, 1. Oh. Okay, still finds that GT. Semicolon. Oh, okay. Varying from digits, maybe digits. There's digits. Oh. Ooh. Less than. Less than. Good. Less than. 5 percentage. Exactly. Percentage. Wow. I found it. So, you know, if you, it goes all the way to the end. I think that's the end. So the trick is if the character sets include all the possible symbols that appear as a point, it will not break into the middle. Anyway, it's harder than I thought. But this example is kind of unique. Anyway. Okay. Okay, let's continue. So the rest of the questions in the homework is text modeling, and it begins with, it uses this data set. Let's get to understand this data set a little bit. It's an academic data set that has 10,000 rows, close to 10,000, and then 6 columns. So what happens here is I downloaded the data from an academic database, which are these academic papers. And here's a question. Here's a trivial question. Later on, as you work on this problem, then you'll get to see the content. Well, maybe later today, we'll see the content. And then if you figure out the academic discipline, it can be anything. You know, it can be math, it can be geology, right? That's all the subjects. It can be business as well. If you figure out the discipline, let me know. Okay, these are all from one discipline, but rather broad discipline. So here, what are these data? All of these are pretty short. I guess now all of these are most of these are objects. They are text, but most of these are rather short, but except for one column. The abstract prepared is the cleaned version of the abstracts of these academic papers. So it can be long. It can have 100 words. So it can have, you know, 1,000 characters or so in each of the entries. And then you also have subjects. These are the keywords specified by the journal about each of the article. And subject count, number of subjects that counted. You have the article title and you have the journal title. So, and there's no missing values. Let's take a look at one of these value. So if we look at the first row, but then we look at the abstract prepared, this is one example. So, you know, this looks bizarre, but I'll explain what happens here. To begin with, when you look at this data, try to ignore the slash 2 capital letters. Just try to ignore it. Then you see words: increase recognition, social phobia, common, deliberate, debilitating, disorder, develop. So what happens is, I think there's an original version. So this is the original version. Anyway, this is better. The original version of the abstract is this: with the increasing recognition of social phobia as a common blah 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 disorder. That's the original abstract. And the data first go through a round of cleaning for those special symbols. But in this case, there's not many special symbols here because it's downloaded from database. It's not downloaded from scraping the website, right? So it doesn't have those HTML codes. These are clean, pretty clean data because this is human readable languages. And then it goes through a series of steps to prepare the data, which includes tokenization, stop words removal. I'll talk about that a little bit. And also go through one step, which is called lemmatization, that recognizes the point of speech of each words and then adds those tags. So that's why you see these slash, that's verb, slash verb, slash noun. So these words are analyzed by the program and designated as a type of function words. You know, so but if you compare these words, you see that with is gone, increasing becomes increase, recognition stays, of is gone, social phobia, as is gone, a is gone. Those words that are gone are what we call stop words. These stop words, we use them in our language, but they don't carry special meanings. These are words to make communication fluent. All right. But it, you know, from a message point of view, it probably doesn't carry too much, too much information. What we care here is the information. We want to retain those words that are only informational, informing, because our computational resources are limited. All right, and because of this, after cleaning, and also you notice that everything here is lowercase, except for the point of speech designation. So everything is turned lowercase. It's one of the techniques that we use to also, again, reduce the complexity. All right, so the original data set becomes the processed, prepared data set. And the preparation is, and why I talk about these is because I want to briefly touch on the preparation steps. So data from the web needs to go through cleaning for the special symbols. Data from databases typically don't need that cleaning. So what happens after you clean the special symbols would be to prepare the text data. And here, these are the steps these are common steps that we'll need to go through for raw text before the text can be used in a text model. The LDA, latent dirichlet allocation model, is a text model. So these preparation steps include tokenize. Tokenize means to break long sentence into each individual words. Okay. And why do we break them into the individual words? I'll talk about it later as we talk about the text model. So that's tokenize. And after tokenizing, you have these individual words, individual tokens. And then with each of the token, we can further process, such as we convert them to lowercase, which doesn't require you to tokenize, but we do it at the same time. But one important thing to do is to filter words by the length in a way that you retain, you increase the potential information that's retained by retaining these tokens. Or in other words, you try to drop those tokens that probably is not going to be informative, such as those tokens that are super long, a word that has 30 characters, let's say. Those kind of words may only appear 1 out of 100,000 times. If it only happens one time, how can you see the correlation with other words? Those words are so unique that it's not going to be useful. So you want to limit those words to all those, more commonly used words. Those words that has length, that's more common. So if you take a look at distribution of the length of characters, and most of them falling to between 3 and 15 characters, anything that has only 2 letters, it's not very useful. ANN, right? Or a book. Same thing with saying book. Not very informative. And same thing with the longer words. So filtering those words that have very short length or very long length is one of the steps. All right, and then dropping of the stop words. Stop words don't carry meanings. Words like these. There are about 250 stop words in English. So words like this, a, and, the, this, that, things like that. It needs to be removed. And the last step, maybe lemmatization, is to recognize the point of speech and also to shorten the word into its original form. Plural becomes singular, and then singing becomes sing, because that's a base word. Sometimes it's not used, sometimes it's used. It kind of depends, but typically, as a little bit more background here, you can read for yourself. So there are multiple packages that we can use. GenSim is something I find quite useful and user-friendly. It's especially, it provides pipelines to streamline the preparation stage. So I opt to use GenSim. This part I will not go into detail because there is because the demo has extensive examples on preparations. It also has extensive examples about regular expressions. And for that, the video goes into length. So the video uses these examples on different data sets, but same kind of examples. And that would be all about cleaning. After cleaning, there's preparation stage. This is the slide demo 5. In the preparation stage, it goes into detail using other examples. So I encourage you to go through these by yourself, mostly by using the slides demo. It demonstrates each of the step by step, and then in the end, it constructs a pipeline that puts them all together. The reason I don't go through in a class is because there's no homework questions about these. So these would be entirely useful if your projects involve them. And our final project doesn't involve text mining. So we'll save a little bit of lecture time. And so all the way it goes all the way from preparation here, preparation to somewhere here. No. All the way to LDA analysis. So that would be the text preparation stage. Okay, study them at your own time. And then we'll continue with the text model. All right, so with this data set, this is the academic data set. It has 10,000 or so papers in the data set. These variables are about papers. And the most important column here is the abstract. So the task is to analyze the abstract after preparation. So these are the words that are retained for each of the abstract. This is one abstract example. By using these prepared words retained from each abstract, we will analyze the text that's conveyed by these words, and to figure out what each paper is about. That's what text mining is doing, but it doesn't read these words. Computer doesn't say, oh, increase, and then increase means to enhance, and recognition means to detect, and then somehow, make use of or make sense of the words like we do. Computers don't do that, right? As you know. So it has to have its own way to model the data. So that's why we have to talk about vectors, terms, vectors, and the LDA model. Let's see. So we have looked at the data set, and then the first question of this part, question 5, I'm not going to go in. I'm not going into details about these questions, but let's take a look at what the tasks are you being asked to do. So there's the count vectorizer. That's a tool. That's a function. Use some function to process the abstract prepared. I just showed you the example. The purpose is to get the feature vectors matrix. Feature vectors matrix, what is it? That's one thing. That's an important thing, actually, in text modeling. When you get that, put it into TF. TF means term frequency. So feature vectors, feature vector matrix, another way to refer to it is term frequency. Feature vector matrix records the term frequency. I will explain. And then, specify the max number of features. So a lot of terms here, a lot of terminologies. What do they mean? That's the purpose of learning the text model. All right. Oh, I just realized I didn't share the Jupyter notebook. Sorry, Miguel. I was talking. Anyway, Miguel is intelligent enough to figure out. But how? Since when? Anyway, so I switched over here, and then I talked about the text model here. But at least all the demonstration about cleaning the text was captured. Hopefully before the break. Anyway, it's only after the break. I switched over. So, latent Dirichlet model. So let's think about this motivating example. How does computer understand the languages or the meanings that are conveyed in these languages? How does computer understands it? Ultimately, we will try to think in a way similar to regression, ultimately. But how to get there? So let's say you have a library, have a millions of documents or books, and none of these have titles. So it's hard to, quickly know which one is about what. There's no title, there's no abstract, there's no keywords, but you do have a computer that can process, that can recognize these texts, and then let's say these are digital books. Computer can recognize the text. How do you really differentiate them? Think wild. Somehow you would have to think in a way, or the computer will have to do it in a way that can connect a document with other documents. If, of these million books, there's this group of book, all of them uses a term that none of the other books mentioned. Okay, so you might have found something that you can use to group these books, right? It's a word that only a few of the books used, but none of the other books used. It definitely will not be the word. Let's see. It definitely will not be the word the, because it's used in every book, right? So words like that would be helpful to discover areas or discover connections between the books. But this is one of the reasons why the is a stop word and will be dropped in the first place when you analyze the text. Those words that are useful are unique, but not so unique. something like that, right? They are common, but not so common. So always in the middle. Those are specialized words that will help you group, bundle, and link documents. By document, I mean book, in this case, right? And by the way, in the case of, in the context of homework, the data set is about abstracts. Each row is one abstract or one academic paper. So one document means one case of the paper, right? So each of the document will refer to either the book or actually the homework is about the abstract. So one document is an abstract or prepared abstract. Here, the document is the book. So now you have come up with a way, that's one word that this group of books used, but none of the other books used. And then you come up with a second word that see if I can visualize it. So with word one, you come up with this group of books, and then you have the complement set of books that don't use the word one. So in this case, with the meaning of word one, you see the commonalities between these books. You know, there's a way to kind of separate them into two groups. And then you go to word two, and then this group of books use word two may have some, you know, overlaps with word one, but not entirely. And then you are able to separate this group of book with the rest by using word two. All right. So with as you discover more and more words, you start to have a way of sectioning the books, right? And that's actually how the library is sectioned. You know, wouldn't you agree? They are sectioned by the topic, by subjects, right? Those are not individual words, but those are bundles, a bucket of words, right? Math papers would deal with, or math books would deal with these concepts about mathematical theories, you know, so such and such. So libraries are sectioned by topics. And topics are basically a list of words, keywords. So you see that words become very important as you start to analyze the text to understand the relationships between the documents. So words represent subject underneath, right? Through words, you can uncover some of the topic space, the subject space. So, you know, word would be the beginning point, but only those words that are meaningful. Right? After you remove words that are not, remove words that are too common or too unique, and the remaining words would be that. If you have a large library, then the remaining words would be immense, would be a lot, be kind of hard to process. So we typically limit the analysis to smaller scales, unless you have supercomputers. In our case, we call those words as feature or term. Do I have it? Features. Okay. Anyway, so word, we call it feature. We call it we also call it token, tokenized, right? Token, feature, term, word, all of these refer to the same thing. So we'll begin with the terms. And as we analyze a problem, we typically have a data set. Each row of that data set is about one document, right? We talked about papers, the abstracts. We talked about the content from the web, Yelp reviews, each of the different cases. And when you put everything together, then the entire data set has, a bunch of documents. And that's what we call corpus. The bunch of documents is corpus. Each of the individual document represents each case. So that's some of the terminologies there. And for each of the problem, we use one data set, a corpus, a bunch of documents. The job of the algorithm is to see the connections between the documents through words. Make sense? That's how we understand, the written materials. That's how we understand languages, by themes and then by words. If I ask you, introduce yourself, what's your interest? And as I hear your words, I start to put them into buckets. And then I come to understand, oh, your interest is, if you name books, then your interest is reading. If you name, movie, your interest is movies and or sports, all kinds of interests. So it is by comparing the words that you say with the words that I have knowledge about that I figure out your interests, the subdomain concept. That's essentially what the computer will also do. But the computer doesn't have background. It starts from scratch. It starts to recognize each of the word and then have a map of the relationship between words and documents. Words and documents. That's the first table that we're going to take a look at. In fact, that's the feature vectors matrix. In a feature vectors matrix, this is the feature vectors matrix that we also call TF, term frequency. This matrix has as many rows as the number of documents. So if your original data set has 10,000 rows, then this feature vectors matrix has 10,000 rows. These row numbers correspond to the document number. Okay, so that's the document on the rows. And then we have the terms on the columns. The terms, and since this is a matrix, this is matrix, this is the think about it as a NumPy array. It's sparse array, but think about it as NumPy array. It doesn't have, it's not like data frame. It doesn't have the indexes. It has indexes, but it doesn't have the column labels. It doesn't have rich text metadata. So the only thing you have is the order, the index position 0, 1, 2, 3, etc. on the columns. Anyway, the columns will correspond to the terms. So let's say if we model as many as 1,000 features, which means to analyze this problem, given the data set, we only retain the most frequent 1,000 terms after removing stop words, after limiting our words to those whose length is between 3 and 15, common length. Okay, after removing all those extreme cases, we might have 5,000 features or words, but we only limit our analysis to the top 1,000 words. So that's the specification that you make by the model. Let's stick with that for now. We limit our analysis to the top 1,000 words. So this matrix is going to have 1,000 columns. Each one of them correspond to one of the features or the term that we focus on, right? One of the 1,000. So you have rows and columns. The rows are documents, the columns are words. So what is the content of this matrix? What are the values? It's integers. It's 1, 2, 3, or 0. Maybe not 0, but 1, 2, 3, 4, 5, 6. It's a relationship between document and word. What is this relationship? It's a frequency. So that's why it's called term frequency. It's the frequency of different words that are detected in each of the document. Given the document in the row and given the feature or the word in the column, how many times does it appear in that document? That's term frequency, right? Or that's feature factors. What is feature? Feature is the words, and feature is represented in the column. So each column is a vector, it's a feature vector. That's why we call it that way. All right. Why do we model like that? Now, obviously, words carry meanings. So by knowing, by keeping track of which words appear how many times in which documents, we can come up with a way to mathematically, model the relationships between the documents if they have the same patterns of words. So, essentially this feature vectors matrix records which words appear in which documents for how many times. This is called bag of words. Each document is represented as a list of words that appear a certain number of times. That's a baggage of words. But there's an important limitation here, which is by using a tabular form to represent bag of words, something is lost. The sequence of the words is lost. It doesn't matter whether or not gold, G-O-L-D, gold, as a word that appears in several of the documents, it appears in the beginning of the text or the end of the text. You only count the number of times. It is the number of times that this word appears in the document that matters. Nothing else matters in this way. Think about it. Does order matter? I would think so. The way I speak, why I say the first thing I say, why I say the last thing and the last, there's a reason. And our languages follow you know, some kind of, or at least we say important things first. And then there's logical reason, you know, let's say, I hate Ghost, that's why I don't, you know, like to play this game. There's a logical expressions here that you know, that can be helpful for language models, but it gets lost. All right. So if that's lost, what do we gain? It's important to care about the sequence of words, but to model it would be immensely difficult because there are so many possibilities, right? You can put orders in there, but then each word will have a different order, and then we'll have multiple order, you know, records because the word appears multiple times. How do you model something like that? A lot of information, it's hard to, you know, it's hard to use a tabular form to really model it. So the trade-off is that by ignoring the word sequence and only focus on the number of times the word frequencies, there's at least something that we can gain to analyze, you know, the relationships between the documents. And at this point, let's take a look at the homework. There is a question here, question 7, that asks, why is the term frequency representation, which is the feature vectors way of modeling the relationship of documents, why is this representation called a bag of words? In other words, what does it assume? Right. This question is about what I just said. It assumes that by using this representation, it assumes that the sequence, the order of the words, will not be considered in the model. It's not so much that it's not important, but the model is not able to model that, to represent that. So this representation would mean that the order of the words is not relevant. Right, so that's what this question is about. Okay, there's an important thing here. So if the columns are words or terms or features, and the features are actual words, gold, silver, you know, bag, any other examples. But these matrices, their columns, you cannot assign a column label there. You cannot say this column label, this column name is gold, that column name is silver. You can only use, I mean, index positions. How do you represent that? How do you, I mean, how do you link the index with the actual words? To do that, we will use the several data objects here. In this case, it would be, if you look at the demo material, the object that we use is, we first use count vectorizer to model all these different features, and we get a count object. So what it does is it will encode This is an encoding process. It will encode every unique words as it starts to process the texts. For every unique word, it will assign a unique number. And then as it goes through the entire text, the corpus, for every word that it encounters, it will record the number of times that it appears in which document. So basically, it's the raw data behind the term frequency table. And then because each unique word is assigned a unique number, beginning with 1, I suppose, beginning with 0. So when it constructs a term frequency table, it will map the order of the column to the unique number for that word. And all those information, you can extract that by getting a list format of the different words whose index position corresponds to the columns here. So you have a nice representation of which column maps with which word feature, and then you can call it by using the order of the index of the column. So we call that what do you call that? We call that feature names. Let's see. Feature names. Feature names. It's not here. It's in the hands-on. We'll talk about that more. But one of the exercise is to, and this involves the topic. We'll talk about topic next time. Topic is another dimension of concept here. Topics is something like what I say, refer to as interest. So if I ask you to introduce yourself, you talk about a few, examples of what you do, your hobbies, and then I can quickly figure out what those interests are. You like reading, you like movies, you like sports, which kind of sports. These are topic. Under each of the topic, you would use certain words than other words that are used in other topics. Straightforward, right? So this is a dimension space that's modeled in the LDA model. And so for one of the homework examples, I will ask you to figure out what is the most likely topic of each of the abstract, and then given that topic, you will extract the most frequently, or you will extract the words that has the highest weights under this topic. Let's say movie. If it's a movie, then under with that interest, what words will typically appear? That appears most frequently when people talk about movies. We'll talk about theater, we'll talk about popcorns, things like that. So as examples. So for the homework examples, you will figure out, given a topic, what are the words that appear that has the highest weights under this topic. So for that, you will get the index positions of those words. And then given the index positions, you will use the feature names list to extract the actual words. There are several tables here. There's a feature vectors matrix, or TF table here. And later you will have a feature name list. And then you also will have a, once you have the topics from the model, then you will have the topic document, let's say, document topic table. And then you also have a topic term table, so multiple tables, the multiple data objects from the model. We'll start to talk about that model specifically next time. And then I will also talk about the rest of the homework questions. And with that, I think that'll be all for today. Okay. Any questions, let me know. Oh, let me remind you that it might be a good time to start working on your projects, and let us know whenever you have questions. Don't delay. When you have questions, shoot it out, ask us, and then don't let that be, the reason that project gets delayed. All right, with that, let's call it a night. Hey, Miguel. Class is finished.
Yes, sir. Thank you.
All right, have a good night.
You too. Bye.
Bye.